Did you get the same thing as I did? Low d high minus high d low. At least you said it right? Mm-hmm. Okay. Now we follow the ddx. That's all this calculus stuff is about. Follow the ddx, go slowly, precisely, get the right derivatives as you're going. So we have the formula set up correctly. Just follow the ddx and show your work. Now, if you try to do too much stuff in your head, I swear it's really hard. You got to go slowly and write lots of work out. I know that takes a tremendous amount of paper, but trust me, it's worth it. You want to get the right answer slowly rather than the wrong answer quickly. That'd be the wrong way to go. So here we'll have, do I take the derivative of 1 plus cosine x there? No. I need parentheses still because I'm multiplying. Times the derivative of sine x. What's the derivative of sine x, folks? Good. Okay, got it. Minus, I don't take the derivative of sine x, but I do take the derivative of 1 plus cosine x. What's the derivative of 1 plus cosine x? What happens to the 1? A derivative of 1 would give you 0, then you do the derivative of cosine, that's going to give you a negative sign. So we're going to be multiplying here by negative, make sure it's in parentheses because you're multiplying by a negative there, you're not subtracting, multiplying by a negative. Sine x. All over, don't forget about that bottom, 1 plus cosine x squared. How many people made it that far? Good. Hey, calculus is done. Right? As soon as you finish that, there's no more as soon as there's no more ddx's, your calculus is over with. Now it's just algebra and manipulation of those rational expressions. Well, not even rational. Those expressions right now. So our trigonometric rational expressions. So if we distribute here, we're going to get cosine plus good. Then what?
Plus sine squared. Sine squared. Sine squared.
Sine x squared is not the same as sine squared x. This,
you're squaring your sine.
this is not. That is not the same thing. If you're putting that, this is an angle right here. We're actually squaring the sine. This is the same. Sure.
That's what I was writing.
that is that, right? But if you omit those parentheses,
now you got something.
This is wrong. Okay, this implies this. That would be incorrect. Okay, you can't do that. You can't change those angles unless you actually use one of the formulas to change angles. So we're going to put our sine squared x like that. Are you all right with that so far? Cool, cool. Tell me something awesome that happens.
Sine squared.
Yeah, trigonometry is awesome. It's happening right now. Calculus, also awesome. It's happening right now. But something even awesomer.
Identity.
Yeah, what identity? You need to see the identity.
Mm-hmm.
What's this give you? 1. That's a 1. Cosine squared x plus sine squared, unless I'm wrong. That doesn't happen very often. Just kidding. It happens all the time. But yeah, that's 1. So this is, that was funny and nothing. It must be Monday. You're killing me today. Cosine x plus 1 over 1 plus cosine x squared. Give me something else.
Take off the square at the bottom.
Can you cross those out? Do you see how they're one entire term right now? Well, factor, I suppose. One entire factor here with here. So that and that is gone. What's on our numerator still? And that's our derivative. Would you raise your hand and feel okay with this one so far? Good deal, all right. What did we just find again? That is the derivative. What is a derivative? So we found the slope. That's a slope function. If I asked you to find an equation of a line through a certain point, you'd use that for your slope. You'd plug in your value to that to get your point, and then you'd use y minus y1 equals x minus x1. Same ideas. Are you guys all right with this so far? By the way, if I asked you for So a different example. That, could you do it? Okay. What does that mean, by the way? Just a second derivative. Let's take the second derivative. So let's find that. What's the first derivative, please? Okay, let's find the second derivative. Sure. Derivative of cosine is negative sine x. What's a third derivative? Say it again. Negative cosine x would be the third derivative. Are you with me on that? Negative cosine, because if we have negative sine x, the derivative of sine is cosine. This is negative cosine if I take the derivative. How about the fourth derivative? Why? Derivative of cosine is negative sine. Negative times a negative gives you a positive sine. That's interesting. It's really weird. How about the fifth derivative? 6. Let's see. Fifth derivative, sixth derivative, 7, 8, and back and forth. Oh, it's cyclical. So when we take the derivatives of sine like that, it's kind of interesting. Unless we have a quotient rule, it is cyclical eventually. By the way, could you have done this if I asked you to evaluate this at x equals pi over 2? What's that mean to do? Just plug that in. You're going to get negative 1 in this case. You with me on that? So we can evaluate also, just don't forget what that means. This would mean that. This is 1, so we have negative 1. Still okay so far? Are you ready to try just a word problem that has this as some of its base? Yeah.
Is y equals sine of x when you take it to the fourth derivative, is that due to the sine of x, sine x period coming back to the same? Coming back, like it shows in the text, the sine of x goes over and it shows where the derivative would occur for sine of x, and does that have anything to do with it oscillating back and forth?
Oh, it has a lot to do with oscillating, yeah. I mean, you got to figure that if the derivative of sine is cosine, that means that the slope of sine is cosine. Right. But the slope of cosine is negative sine. If we keep on doing that, we're just finding, basically, the fourth derivative is a slope of the third derivative. If the third derivative is negative cosine, we're going to be getting sine out of that, which is it's an interesting problem, but it does have to do with the relationship between sine and cosine.
So I think he's talking about the graph, like how it goes up and down like that.
Right.
Yeah.
Whether the fourth derivative has to do with that?
Where it oscillates, where, because it comes back to the same position once you go 4 times over.
We're not moving.
Oh, we're not?
No, we're not.
He's talking about the f(x) graph for sine x, how it oscillates.
Oh, I get it. Yeah, I understand how it goes like this. Remember, we're talking about the slope of the entire function. So we're not saying as you go 4 periods to the right or 4 cycles to the right. That's not quite what we're doing. We're talking about the slope of the curve. So, for instance, it's going to be very hard for me to draw this, but this is the idea that we're talking about here. That's sine, right? That's the slope, right? Oh, I messed up. Kind of pretty, huh? In a roller coaster. If you take and graph the value of the slope at every one of these points from here to here, and you say at x equals this point, the slope is this. X equals this point, the slope is this, and this, and this, and this. And you graph those, what you're going to end up with is actually cosine. Here's why. Slope of this point is actually 1. There. Slope of this point is 0. Ah. Slope of this point is negative 1. There. Slope of this point is back to 0. Cosine. Okay. Do it again, you're going to do the same thing, right? Slope is 0. Negative, 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 that's where you're going to get negative sign. Right? You're going to go back and forth and back and forth. You're talking about slopes of things, slopes of, and the third derivative, the second derivative, the slope of the slope function. Fourth derivative, the slope of the slope of this. You're just talking about the slope of the previous function. Does that make sense to you? That's why you're getting these things. You're not moving at all. You're talking about the slopes of your function. That's the idea. Looks cool though, doesn't it? Pretty. Does that answer your question? All right. Now, for a real example, I'm not going to call this a super fun word problem because I got a comment on my little thing that was not super fun. So this is just a word problem. This is a super hard word problem. Hard. It's not. I'm just joking. No sense of humor today at all? Nothing? Honestly? Stand up next time. Maybe we'll get it.
I got that one.
Ah!
Was it one of your followers from Taiwan, or?
I don't know. Okay, so let's say that you put a spring on the ceiling right here, and you attach a weight to it. It's going to stretch a little bit, right? Let's say you hold it real steady, and so it's stretching that spring, and it's sticking there. And one of you jerks comes along and goes, boom, ha ha ha. What's it going to do? It's going to go, right, back and forth. Let's neglect friction of air and all that stuff. Is it going to do that forever? Let's neglect like friction and all that. Is it going to do that forever?
Yes.
Yeah, it's going to oscillate, right? It's not going to lose anything if we just let it go and go and go in a vacuum and stuff like that. Okay, it's just going to do that forever and ever. That's going to mimic a sine or a cosine function. As a matter of fact, if we look at this, I'll write out the example right now. We attach a spring and a mass stretches it 3 centimeters beyond its resting position. A spring is stretched 3 centimeters beyond its resting position. And released. So you go to the thing and go, and it goes, okay, so it's oscillating back and forth. Let's make it at a certain time, at t equals 0. Let's talk about the position function. Let's talk about the position function. If you were to draw this, let's say this would be the spring, and here's the little weight that's attached, okay? And you're going to stretch this 3 centimeters beyond its resting position. So